Is my video visible? Presentation. Is my presentation visible to all of you? Am I audible? Am I audible? Okay, and my presentation is visible, right? Okay, nice. So with this, welcome all of you to the week 3 discussion of this course. This course topic is computer vision, and this is taken by Professor Jayanta Mukhopadhyay, Professor, Department of Computer Science and Engineering, IIT Kharagpur. Myself, Ayan Paul. I am a PMRF research scholar from IIT Kharagpur, and my duties are I will solve some of the question that will be very much similar to your assignment. So whenever you will be solving your assignment, you will not feel something new. Okay. So this is regarding myself. Okay. So with that, let's start the discussion. So in the previous week, what we have discussed regarding real space, projective space, and homogeneous transformation, right? Now in this class, what we will discuss something regarding camera geometry. Okay. So camera geometry, what is this camera geometry? Camera geometry in computer vision, it defines the mathematical relationship between the 3D points in the real world and their 2D projection on the image plane. Okay. So camera, what is the role of camera? The role of camera is to capture an image, right? So your point will be somewhere in the 3D space, and you will be projecting it on a 2D image plane. Okay. So that is regarding the camera geometry, and through models like pinhole camera or perspective projection. Okay. This two are same, means perspective projection is a projection matrix through which we can convert this point in the 3D real world to the point in the 2D image plane. Okay. So that is perspective projection. Okay. Now this is regarding camera geometry. Now what is this pinhole camera? As here this was a word mentioned, pinhole camera. So what is this pinhole camera? So pinhole camera, it is a simplified camera model. Okay. It is the most simplified actually camera model. It is used in computer vision to describe the 3D scene is projected onto the 2D image plane. Okay. Now there are some properties of this pinhole camera. One, the single point, the pinhole camera center through which all the light ray pass. Okay. So that is one of the property or one of the feature of this pinhole camera. Second, a flat image plane. The image plane will be flat. Okay. Where the ray intersect forming an image. So there will be a single point, or also called as camera center, through which all the ray light will pass. Okay. And second, there is a flat plane known as image plane. Okay. Where the ray will intersect forming the image of the real world coordinate. And second, there is no lens distortion, aperture, or focus surface. Okay. So this is the most simplified camera, that is the pinhole camera. Now what are this statement is telling? This is actually a figure, or you can say demonstration, a figurative demonstration of pinhole camera. Okay. So this plane, okay, so this is the point in the 3D real space. Okay. P x comma y comma z is the point in the 3D real space. Okay. And this p x comma y, this is a point on the image plane. That means this point we are projecting on a image plane, and this point now becomes small p x comma y. Okay. So this is the real coordinate p x capital X capital Y capital Z, and that will be projected on the image plane, and that will be now small p x comma y. Okay. Now there are planes. Okay. One is the where the image will form. Where the image will form, that plane is known as the image plane. Okay. That means where the small p x comma y will be there, that will be on the image plane. So this rectangle, you can say, this rectangle you are seeing, this is the image plane. Okay. And this is the real coordinate in the 3D real space. Okay. Now about camera, this is the camera center. Okay, the C is the camera center. Okay, now the camera where it is placed, this is known as principal plane. Okay, the plane where the camera center is placed, that is actually the principal plane or the XY plane. Now there is XY, there will also be a Z axis, right? The Z axis of the principal plane is known as the principal axis. Okay, so again I am repeating, there wherever the camera center will be there will be a plane comprising the camera center. That plane is known as the principal plane, and the Z axis of this principal plane is known as the principal axis. Okay, now what is a principal point? There is another term called as principal point. So what is a principal point? The Z axis of the principal plane, wherever it is intersecting with the image plane, that point, or you can say here, this point is the principal point. Okay, so principal point, this is the O point, is the principal point. Okay, now what is the focal length? Focal length is the distance between the camera center and the principal point. Okay, or where your principal axis is intersecting the image plane, so that is the focal length. So again I am repeating the terms. Okay, so first thing is, let's start again so it will not be confusing to you. First thing is points. Okay, what are the 2 points? One is the real point in the 3D space, that is capital P, x comma y comma z, that is the real point in the 3D space. Okay, now we will have an image point. This is the image point. Okay, that is small p small x comma small y. So this is the image point. So our target is to achieve small p x comma y from this capital P x comma y comma z. So how we achieve it? We achieve it by a help of a camera. Okay, here we are discussing about pinhole camera. Okay, now where is the camera located? The camera center is here. So this is the camera center. Okay, so the plane comprising the camera center, this XY plane which comprising the camera center, okay, this plane is known as the principal plane. Okay, this plane is the principal plane. Now what is the image plane? The point image plane, the plane comprising the image point, that is the image plane. Okay, now now another thing is principal axis. Principal plane, you know, the Z axis of a principal plane is nothing but your principal axis. Now another thing is focal length. What is the focal length? Focal length is the point of is the distance between your camera center and your and the point intersecting the and the point which is formed by the intersection of this principal axis and the image plane, that is this point. Okay, this O point. So this point is also known as principal point. So this is the terminologies regarding the pinhole camera. Okay, now question will be how we can get the xy point from the xy comma z point of the real space. Okay, so that we can achieve by this formula. Okay, so x will be equal to f, that is the focal length, into the capital X, that is the x coordinate in the real space, divided by z coordinate. And similarly y, how y can be found out? That is f, that is the focal length, into the y coordinate of the real space divided by z coordinate of the real space. Okay, so that is how we can calculate the x comma y from your from your capital X, capital Y, capital Z. Okay, so that is the image point from our real world point. So this is the formula from which we can calculate. How it will come? It will come by nothing but your similarity triangle. Okay, so similarity triangle, you can see this triangle and this triangle somewhere like this. I can mark this triangle as well as this triangle. Okay, this two triangle, you can, if I say this is O, let's say this O small p, O small p, this is small p, and C. O small p C will be similar to this. Okay, will be similar to Z. Okay, Z, and then capital P, Z capital P, and this C. Okay, this two will be similar. Whenever things are similar, how we can say f by Z will be equal to this by this. Okay, so f by z will be equal to x by x as well as y by y. Okay, so by that we can get this formula, that is x equals to f capital X by z, y equals to f capital Y by y by z. That is similarity triangle. This triangle and this big triangle are similar. So what does that mean? That means is f, okay, f divided by z, f divided by z, capital Z, f divided by capital Z will be equal to this, you can say this is x divided by capital X, x divided by capital X. Similarly, y divided by capital Y. Okay, so this, by this equation, f, this is f, this is f. So f divided by capital Z equals to x, small x divided by capital X, small y divided by capital Y. So by this we can get this formulas. Okay, so this is regarding the simple concept of pinhole camera. Now we can say what will be the mapping matrix. Now we are thinking about mapping this point, that is x comma y comma 1 y1, because this px comma y, this is a 2D point and that is denoted in non-homogeneous space. Non-homogeneous space means we do not include a scale associated with it. But now what we are doing, we are associating a scale with it. Okay, so that is why you can see it is a two-dimensional point, right? So it will be x comma y. But in the previous class, what we have learned is we have two type of space. One is the real space, one is the homogeneous space. Real space, homogeneous space, or whatever we called as projective space. Okay. So two type of projection we can get, real projection as well as this homogeneous projection, or real space and well as this projective space or homogeneous space, what you call. So in this diagram, what has been shown, has been shown the coordinates of real space. But whenever we are changing it to an homogeneous space, how we write it? We write by adding one extra coordinate, and that is nothing but your scale. So that is why x comma y is written as x comma y comma 1. Similarly, this is the point in the real space, and that is written previously as x comma y comma z. Okay, so that is a real space point. But now in homogeneous space, how we write? X comma y comma z comma 1. Now we have to map this to actually we will be given this and we have to find this. Okay, so how we can do this? We can do this by just multiplying it with this matrix. Okay, so just multiply, either you just do it directly with the formula, or in matrix multiplication, how we show it? We show it that this point will be multiplied by a projection matrix or projective camera matrix. Okay, that is known as P. Okay, so that is how we write this projective camera matrix. So what is the you can say what is the order of this matrix? The order of this matrix is 3 cross 4. That means we have 3 rows and we have 1, 2, 3, 4 columns. So that is 3 cross 4. Okay, so 3 cross 4, and what is the order of this? That is 4 cross 1. So our 3 cross 4 and 4 cross 1. That means our resultant vector will be formed as 3 cross 1. So this is the resultant vector. Okay, so we will be given this point and we have to find this point. Okay, so how we can find? By this projective matrix or projective camera matrix. Okay, so this is the thing. Now this matrix can be written in this form also, that is multiplication of this 2 matrix. Okay, why this is important? Because you can see this matrix will become a diagonal matrix. Diagonal matrix means we have only elements on the diagonal. So that is why, that is how we write. And why this matrix is important? This matrix is a combination of 2 matrices. Okay, so we can just divide this. Okay, so this you can rightly see, this is a identity matrix. So this identity matrix, and this is a 0 column vector. Okay, so this 0. So that is how we can also write our projection matrix. So this is regarding the pinhole camera mapping. So is it clear to all of you? Is it clear to all of you? The formulas and all? The formulas, the terms, is it clear? It is the basic thing and I hope it is clear to all of you. Clear, right?
Sir,
Yeah, please.
clear, sir, clear.
Oh, now let's move on to the next thing. Okay, this is the very simplistic form. Now let's make it a bit complicated. Okay, how we can complicate it? We can complicate it by putting the origin. Okay, the origin in the image plane is actually this origin. Okay, but now we are shifting the origin of the image plane, or origin of the image plane is also known as what? Principal point, right? So now what we are doing, we are offsetting the principal point. What I have told you, what is a principal point? Principal point is the point of intersection of the z axis of the principal plane with the image plane. Okay, so that is known as principal point. That means O, or the origin of the image plane, is your principal point. Now what we are complicating our thing, we are offsetting the principal point. Our earlier this O is our principal point. Now we are slightly offsetting the principal point. Now our principal point is somewhere located here, that is O dash. So now how our, okay, someone is joining. Okay, so now how our equation changes, that you have to understand. So now earlier what is our equation? Our equation is this equation. Okay, x equals to f into capital X divided by capital Z. Small y equals to f capital Y by capital Z. Okay, so that is the earlier equation. Now what we are shifting? We are shifting this x and y point to something known as x dash and y dash. Now how we can guess x dash and y dash? If we know how much we are shifting. So how much we are shifting, that offset we know, that is px py. Okay, so again I am repeating, earlier our principal point or the origin of the image plane, that is O, but now we are changing from O to O dash, that means we are offsetting the principal point. Okay, so now how our equation will change? Our equation will change. Earlier we were calculating only x and y. Now we will be calculating x dash and y dash, because we have shifted some shifted to some offset. Okay, what is that offset? That offset is nothing but px comma py, small px comma small py. So earlier our image point was x comma y. Now our image point will be x dash comma y dash. What is this x dash? X dash is nothing but px plus x. Y dash will be equal to py plus y. So this is the only difference. So earlier we are calculating just xy. Now we have to add plus px and plus py. So this is what our changes is if we offset the principal point. Okay, so this is the logic. Now what will be our projection matrix? Our previous projection matrix is this, but now we have introduced the new terms px py, that is we are offsetting the principal point. So that is why earlier this is our projection matrix f000 0 f00 0010. This was our projection matrix. Now as we have offset the point by px and py, so our new projection matrix or projective camera matrix, this is our new projective camera matrix. Okay, so what is the changes? Earlier we have f0000. Now at the third position we will have px, and at the third position or the third element of the second row we have this py. That is the changes. Okay, so this is the change. And again we can write we can divide this matrix into the into two separate matrices on multiplication of two matrix. So this is one matrix and this is another matrix. Again this will be identity, this if I divide, this portion will be identity matrix. This is a zero column matrix, so I comma 0, and this matrix is known as k matrix, that is the camera calibration matrix. So this is the changes if we offset the principal point. So up to this, is it clear to all of you? The changes clear, right? Any doubt regarding this? This is the most simplest equations, so you should understand these things fully. So any doubt regarding this? No problem, you can ask, because questions will be based on this. So you can ask me if you have any doubt. No doubt, right? Okay, so let's move on to the next thing. Okay, so let's move on to the next thing, that is shifting of the world coordinate. in the previous thing what we have done, we have offset the principal point, or we have shifted the principal point. Now what we are doing, we are again complicating a bit. So what we are doing, we are also shifting the world coordinate. So earlier our world coordinate is based on the principal plane only, that is this plane. Now we are again changing the world coordinate to this. That means we are, what we are doing to the world coordinate, we are we are just translation, we are giving a translation, and we are also giving a rotation to it. So again I am repeating, earlier this was our principal plane, okay, but now this is our principal plane. That means we have given some translation to it and some rotation to it, right? So that is why we have introduced these two things, rotation as well as translation. Okay, what is this? This is very simple. I have told you that whenever we are talking about homogeneous coordinate, we are only adding a scale to it. That is, we have added 1 to it. That is how we can transform this in homogeneous coordinate, or you can say coordinate real space projection to this homogeneous projections. Okay, so this is something very simple notation. Again I am repeating, whenever I will be using this notation, that means our point will always be in homogeneous coordinate, and whenever there is a tilde after it, so that means our point is at the non-homogeneous coordinate or inhomogeneous coordinate. So this is the just a notation. Okay, so again shifting our focus to this. Now how our this projection matrix will change, that is what we need to know. So now what we have done, we have introduced this rotation and we have introduced this translation to our previous this projection matrix. So earlier our projection matrix was k into I and k into I 0. Okay, so that is how we previously written. So let me show you k I into 0. So earlier this was our projection matrix, but now as we have given rotation as well as translation to it, now our projection matrix will be changed to k, that camera calibration matrix, or k will remain same, but this thing will change. Okay, this thing will change. This thing, how it will change, it will in the first, let me show you. In the this we have only identity matrix, but now in place of identity matrix we will have a rotation matrix, because we have rotated the principal plane, and then in place of this 0 column vector we will have a translation matrix, because we have translated the plane also. So this is the changes when we are shifting the world coordinate. Okay, now about CCD camera. CCD camera is based on that same logic, shifting of the world coordinate only we have some additional changes to it. What additional changes to it? Whenever we are talking about the CCD camera, this portion will remain the same. That is, we have shifted the world coordinate. Okay, so first regarding CCD camera. So CCD camera, what is the full form of it? Charge coupled device sensor. Okay, so this is a type of sensor that capture image, and how this physical process is mathematically modeled in computer vision to relate 3D world point to 2D image coordinate. These things will remain same. This definition will remain same. Only you have to understand what is the CCD camera model. So that is charge coupled device. So what does CCD camera model introduce? So earlier CCD camera model are change in the world shifting of the world coordinate will remain same. That means this portion will remain same. Now what will be the changes about? The changes will about the K matrix. Okay, that is the camera calibration matrix. How the things will change? Now we have earlier f and f according to our previous discussion, that is focal length. Now as in the image, due to the CCD camera, our focal length will be changed with the number of pixels per unit length. So that is why we will be introduced, our f will be changed to alpha x in case of x direction, and alpha y in case of y direction. Okay, so earlier it was f0 px, 0 f py, and 0 0 1. Now it will be f alpha x alpha y in case of f. Okay, so this is the only. And what is alpha x alpha y? That is f dot mx and f dot my. So this is the changes. Another change, this position earlier it was 0, but now in this position we will have s equals to tan theta. That means our this sensor is not parallel, but it is at some angle theta. So that is why we will also introduce S here. So earlier this was our calibration matrix. Now our calibration matrix changes to this in case of our CCD camera model. So this is the only thing. Okay, so let me clear some summary with this. So earlier in our basic discussion, this is our matrix, that is K I0. K, we also don't call it K. Earlier it was diagonal FF1 and I0. Then we have changed to changed our discussion to offset of principal point, and when we have done this, our this will remain same, but this diagonal FF1 changes to K matrix. This K matrix is known as camera calibration matrix when we have offset the principal point. Now what happened in shifting the real coordinate? Shifting the real coordinate, K remains same, but the next matrix, that is I0 or identity matrix and 0 column vector, that changes to rotation matrix and this translational column vector. Okay, so this is how when we have shifted the world coordinate. Now in case of CCD, this RT will remain same, this portion will remain same, that is rotational matrix and this translational column matrix. Only our camera calibration will change. This K matrix will be now changed to this. So this is the summary of it. Okay, now the thing is, most important thing, this thing, okay, that is the projection matrix P. This is our main concern, because this matrix will only transform our real coordinate in 3D space to the image point. Okay, so this is our main focus. So this is very important matrix, that is the P matrix. So let's see some of the characteristics of the P matrix. P matrix, you say how many degree of freedom will be there for P matrix. Now in case of translation, we will have 3 degree of freedom in case of translation. Similarly for rotation, we will have 3 degree of freedom. And about K, that is the camera calibration matrix, you can easily see in the picture 1, 2, 3, 4, 5. This one is just for scale, so 1, 2, 3, 4, 5. That means 5 degree of freedom. So in total, this P matrix will have 11 degree of freedom. So again I am repeating how 11 degree of freedom, P equals to K into this RT matrix. Okay, so K matrix is this matrix. This matrix we have 1, 2, 3, 4, 5, 5 degree of freedom. Okay, rotational matrix we have 3 degree of freedom in case of rotational matrix. Translational vector, we will have 3 degree of freedom in case of translational vector. So our total will be 5 plus 3 plus 3, that is 11 degree of freedom. So this P vector or P matrix will have 11 degree of freedom. Out of this, whenever we are talking about K matrix, okay, this K is the camera calibration matrix. Camera calibration matrix means this parameters are internal, means this internal or intrinsic parameters. That means this will only be decided based on camera. So that is why this intrinsic parameter will have K matrix will all this intrinsic parameters. So that is why this intrinsic parameters are 5. Similarly, whenever we are talking about extrinsic parameter, how this extrinsic parameter are formed? That is formed by the rotation and translation of the principal plane. So that is why these are extrinsic parameters. So extrinsic parameter are 6. So again I am repeating, this P matrix will have total 11 degree of freedom. 11 degree of freedom, this K matrix will have 5 degree of freedom, and this RT matrix will have 6 degree of freedom. This K matrix is camera calibration matrix, so that is why these parameters are intrinsic parameters. RT are found by this rotation and translation of the principal plane. So that is why these are known as extrinsic parameters. Okay, so this is about P matrix. Now again we can write P matrix in this form. Okay, not in this form, but we can also write in this form also. So now how we are writing it? What is the total number of elements in case of this P matrix? That is 3 cross 4. That means we have 12 parameter, right? 3 cross 4. So first 3 columns is the M matrix that we can write, and last column we can write it as P4. Okay, so by this also we can write this P matrix. Okay, so this form is important, that I have already discussed again and again, and again we have this form. Okay, this form, how it shows, this form it shows by this M is a 3 cross 3 matrix, and this is a P4 is a the fourth column of this P matrix. Okay, this M consists of first three column and this fourth column by P4. So that this two this by this two notation we can denote our P or the projective matrix. Okay, now if we are interested in finding the K inverse of this K inverse of this matrix, that can be calculated by this formula. Okay, this formula. Simply, if you will be given, just you can find out the inverse of the matrix and you will be finding the K inverse matrix. The property of the K inverse matrix is the matrix will be formed as a upper triangle matrix. That means below the diagonal the all elements will be 0. So this is a property of the K inverse matrix. Okay, so this is regarding your camera geometry. So is it clear to all of you, whatever I told you? Is it clear? Am I audible?
So can you
Yeah,
so
please.
can you explain what is this K inverse?
K inverse, the inverse of the K matrix. The inverse of the K matrix. K, you know, na? K is the camera calibration matrix. So inverse of the K matrix, there is a property regarding inverse of the K matrix, that whenever we are doing K inverse, we are getting a upper triangular matrix. So this is a property of the K inverse matrix. Okay, simply no need to even memorize the formula also. If you are given K matrix, you can easily find out the K inverse matrix by simple inverse of the matrix. Okay, so this is regarding this. So is it clear to all of you what we studied so far? First pinhole camera basic, and then offset of the principal point, then shifting of the real coordinate, and then CCD camera. Okay, each we have the unique P matrix. Okay, in the first we have a very simplified P matrix, then we have complicated it by adding Px Py, and then by rotation and translation we have shifting to world coordinate, and then CCD camera we have changed the K matrix a bit. Okay, so these are the four things. So I hope it is clear to all of you. Now let's discuss the next thing. Okay, estimation of the projection matrix. So I have told you about projective matrix. Projective matrix, how many degree of freedom we have? We have 11 degree of freedom. Total 12 elements, but one is for scaling, so we will have 12 degree of freedom. 5 for intrinsic, that is the camera calibration matrix, and 6 for extrinsic, that is rotation as well as translation. 3 for rotation, 3 for translation. Now the question is how we can estimate the projective camera matrix. Okay, so that is the question. So how we can estimate it? How many points do we require for it? So if one point will give us two equation, then to solve 11 variables, we will be needing 11 equation. So if one point will give us two equation, then how many equation we will need, or how many points we will need rather? So again I am repeating, projection matrix means we will have 12 elements. Okay, 12 elements, one element is a scale factor, so let's ignore it. So we will have 11 elements or 11 degree of freedom. So to solve 11 degree of freedom, how many points we require? If one point will give us two equation, so that means 6 point will give us 12 equations. So by that we can solve the projective matrix. Now how we are forming the equation? So you know xi and this pxi. Xi is the image point, right? And pxi is also the image point whenever we are doing the projective transformation to it. So if we are just multiplying the pxi, sorry, not multiplying, but cross product of this will be 0, because it will lie on the same line. So that is why we know if two points lie on the same line, and if we do the cross product of it, it will be 0, right? There can be change of scale, so that is why I am not mentioning equally same point, but it will lie on the same plane as it is, because there can be a okay, someone is joining. There can be a difference in the scaling, but whenever we will be cross product two points that will be that are lying on the same line, so its answer will be 0. Okay, so by this equation pxi xi into cross product of the point, we will be getting 0. So by this we can get the equations. How we can get the equation? Xi we know, that is the whatever the points are there. Okay, and pxi, p is nothing but we can write it like that. Okay, this how it is written, 3 rows are there because 3 cross 4, right? So 3 rows are there, so that is why this is the first row, this is the second row, this is the third row. Each row will have 4 elements. Okay, so it is actually 1 cross 4 here, 1 cross 4 here, and 1 cross 4 here. So this is actually our 3 cross 4 matrix only. So this we know, and we know the xi, and we can multiply by xi. So actually this is xi, yi, wi is our image point. Okay, and what is our this xi will be xi. Okay, that is capital Xi, and this small xi will comprise of xi, yi, wi. Wi is nothing but for scaling, because we know the image point is 2D coordinate, but wi is for scaling, so that is why it has been written wi is nothing but for scaling. Okay, so this is thing. So if we multiply it, we will be getting this. Okay, this is how we can multiply it. You can just go and check after the class. So this is how we are multiplying it. So we will be originally we will be getting 3 equations. Okay, because these are the three variables, and this, so whenever you will be do this into this into this, and this into this, that is simple matrix multiplication. Again I am repeating, this you will do this you will do this you will do this. That means 3 row and 1 column. That is why will be getting 3 equation. But what we understand from this is actually the third equation that will be formed, that is a redundant equation. That means third equation can be formed by our first equation and second equation. So that is why third equation is a redundant equation. So that is why we are left with only 2 equation. So 2 equation, each point will give us 2 equation, and 2 equation we will require 6 point to solve the matrix, because our matrix has 11 DOM, that means 11 variable. So that is why 2 equation for each point we are getting each point we are getting 2 equation for each point we are getting 2 equation each, and we will be needing 6 point to get the 12 equation. So by this 12 equation we can solve this P matrix. So this is the idea behind this. So again in short, very short, if I explain you, so our DOF is 11. That means how many equation we will be requiring? We will be requiring exactly 11 equation to solve all the variables to get the P matrix. Okay. Now for getting this 12 equations, how many point we require, that we have understand from here. How we understood from here? Each point will be giving us 2 equations. So if we are getting 6 points, so 6 into 2, that is 12 equation. By 12 equation we can solve the P projection matrix. So this is theory behind our estimation of the projective camera matrix. So is it clear to all of you? Clear, right? Okay, nice. So this is the theory regarding this estimation of the projective camera matrix. 11 DOF means 11 parameters, 11 equation. For getting 11 equation we required 6 points, because each point will give us 2 equation according to our this matrix. Okay, so that is the theory behind it. Now let's move on to the next thing, that what is the property of this P matrix. Okay, so P matrix, again it has been written in this form, that is, someone is joining in this form, that is in this form, that is PM P4. That means M means the first 3 column comprising the P matrix, and P4 means the 4th column comprising the P matrix. So that is how we can write the P matrix also. Okay, now this P matrix can be written as this. This is see, first 3 is M, this portion is nothing but your M, and this is the P4. Also it can be written as like this, that means 3 rows. Okay, so that is how we can denote our P matrix. So there are some properties relating to our P matrix. One is how we can find out the camera center with our P matrix. So it is very easy how we can find the camera center. If we uh, if we multiply the projection matrix with the camera center, the answer will be 0 because camera center is originally at origin. Okay, so the answer will be 0. That means we can get the camera center from here. P into C. If we do P into a matrix C, or rather I can say a point C, so we can get the camera center. Okay. Now, if in this case, if our M is non-singular, that means whenever we are doing determinant, if that will give us a value, not 0, so that is known as non-singular M. Okay, so in that case, we can understand that that our camera center is at a finite point. If our M matrix is coming 0, okay, in that case our camera center will be at infinity, or our camera will be at infinity. So this is the logic regarding camera center. Okay, this is the second thing about column points. Okay, so each vanishing points of x, y, and z can be found out by multiplying p1, p2 and p3 with x, y, and z. That means how we can find the vanishing point in the x direction? Very easy. If I can just multiply the whole projection matrix with 1 0 0 0, so I can find the vanishing point in the x direction, capital X direction. Similarly, how I can get the vanishing point at y direction? Very similar. This projection matrix into 0 1 0 0. Similarly, how I can get this vanishing point in the z direction? It is very easy. This projection matrix into 0 0 1 0. Okay, so by that I can calculate our column points. Okay, now what about if I multiply p that is projection matrix into 0 0 0 1? In that case, what I will be getting? I will be getting image of the coordinate origin. Okay, so image of the coordinate origin I can get, because 0 0 0 is nothing but our coordinate. Okay, 0 0 0 and 1 is nothing but scaling factor. So if 0 0 0 I need to find the image of 0 0 0, I just need to multiply this by 0 0 0 1, and that will be nothing but p4. So again I am repeating how I can get vanishing point of x. That is nothing but p1 is the vanishing point of x. How I got it? By multiplying p with 1 0 0 0. Now how I can get vanishing point in y direction? That will be nothing but p2. And how that can be found? P2 equals to this projection matrix into 0 1 0 0. How I can find p3 or the vanishing point in the z axis? That will be equal to p3, and that I can find by projection matrix into 0 0 1 0. Now what regarding p4? P4 is actually the image of the coordinate origin. Why image of the coordinate origin? Because this is the projection matrix and this is the real point. Okay, this is the homogeneous form of the real point, that is 0 0 0 1. 0 0 0 is nothing but origin, and 1 is nothing but a scaling factor. So that is why p4 is actually the image of the coordinate origin. Okay, so I hope these 2 points are clear. Now regarding the third property about principal plane. We know about principal plane. So plane parallel to the image plane, plane R3. Okay, so how it can be found out? It can be found out by this R3 t into x. R3 is nothing but this. Okay, that is the third row of the projection matrix. Okay, if I multiply it by nothing but your capital X is nothing but your real coordinate point. So if I multiply it by this, I can find the principal plane. Now about axis plane, we have 2 axis plane. One regarding image at one is the x-axis plane, that I can find out by this r1t, that is the first row into the image into the real coordinate. Okay, that will be equal to 0. That will give me the first axis plane, and second axis plane will be found out by this, that is r2 t x equals to 0. That means the second row of the projection matrix into the original point. Okay, so these are the two axis plane. One is the y axis plane, whenever we will be multiplying it by x, whenever we will be multiplying it by the first row, by that we will be getting the y axis of the plane with the y axis of the image coordinate. And whenever we will be multiplying it by r2, that is the second row, then we will get the x axis of the image plane. Okay, so that is the thing, that is principal plane and the x axis of the image plane. So two axis plane, one is the y axis plane of the image, and second is the x axis plane of the image. Y axis plane we can find out by multiplying this with the actual point, that is x, and by multiplying the second row with the actual coordinate point, we can get the x axis of the image plane. So that is regarding fourth and fifth. Okay, someone is joining. Yeah, so these are the another two properties that we have discussed. Now about property 6, which is again a very important property, that is principal point. So what is principal point? Principal point is nothing but the MR3. What is MR3? I have told you. If M, what is this M? This MR3. So M matrix is nothing but matrix formed by the first, second and third column, that is M matrix. Now if I say third row, MR3 means third row. Okay, R3 means third row. So that is third row of the M matrix. So that is nothing but our principal point. Okay, so that is nothing but our principal point. So that is the thing. Now what about principal ray? Principal ray can be found out by R3Tx. So R12 and R2T we have already discussed regarding the axis plane. R3Tx equals to 0, that is nothing but our principal plane, and this is the principal plane. So this is regarding principal point. So principal point, two axis plane, that is important. Principal plane is important. Column points you have already seen, and another is camera center. Now regarding the depth of a point, how the depth of a point can be found out? The depth of a point can be found out by m into r3t x minus c. What is x? X is your real coordinate. C tilde is your camera center. So difference between this into the direction of your principal ray. What is the direction of principal ray? MR3T is the direction of your principal ray. MR3 is nothing but this, the third row of the M matrix, and R3T is this. Okay, R3T is this. So MR3T is your direction of your principal ray. So these are regarding all the properties of your projective matrix. Okay, so that is how we can find depth of a point. So this is regarding depth of a point. Okay, so this is the thing. So is it clear to all of you? You all understood, right? What is MR3? M is the matrix comprising of first three columns of your projection matrix. Okay, so first three column, if we concatenate, we are getting the M matrix. The third row of the M matrix is the MR3. That is nothing but your principal point. Okay, now if I say MR3, I just do the direction of it. I can get the direction of your principal ray. So that is the thing. And depth of a point, this MR3T and x minus c. X minus c, c is the camera center, x is your real point, and if we dot product with our MR3T, so we can get the depth of the point. So is it clear? MR3 is nothing but the third row, and if MR3T means third row only. Okay, MR3T means third row only. So we are just multiplying it, so that is why it has been written like multiplying it or dot producting it, so that is why it has been written like this. So is it clear to all of you? Is it clear to all of you? At least few points. Is it clear? Okay, now let's move on to the next thing. Okay, so computing camera center. So camera center I have already discussed. P into C will give us 0. Okay, so by that we can get the camera center. So C will be something something P inverse 0. So how we can write it in a more formal way? We can write it in a more formal way by this. Okay, so how our C tilde will be calculated? That is nothing but m inverse into minus of m inverse P4. Okay, so P4 is nothing but our fourth column of our projection matrix, and m is nothing but m inverse is nothing but inverse of the first three column of our this projection matrix. Okay, so this is regarding camera centers. Now there are other parameter like this projection matrix can also be written this M matrix, this M matrix or rather I can say, yeah, this M matrix can be written in this RQ decomposition. RQ decomposition means RQ decomposition K into R. That means K is an upper triangular matrix, R is an orthogonal matrix. I have already told you there is something called RQ decomposition. Any matrix can be denoted as RQ decomposition. RQ decomposition means we will have upper triangular matrix into a orthogonal matrix. So similarly, any projection matrix or any this M matrix can be written like this. Okay, that is RQ decomposition, that is upper triangular matrix into the orthogonal matrix. Okay. Now to get the camera center, this is our formula for the camera center. This is very very important. So camera center will be given by m inverse. If I just move m from this to this side, so minus of m inverse P4, that will give us the camera center. Now for from R we get the orientation of the camera. I have already told you, from R we get the orientation of the camera. From K we get the calibration matrix. Okay, now let's solve some questions so it will be more clear to you. So this is the exercise 1. So consider the following projection matrix. So this is projection matrix that has been given to us. We have been told to compute first camera center, second vanishing point of x-axis, third image point of origin, and fourth vanishing point of the line with the direction cosine 2:3:4. Now can anyone say how can we compute the camera center? Very easy, right? Camera center will be minus of m inverse P4. Okay, so what is this m? So let me show you. Very easy, minus of this equation only. So camera center will be minus of this m. If I take this side, so minus of m inverse P4. So that will be your camera center. Okay, so how we write it? So actually this is your M matrix and this is your P4 matrix if I divide the P matrix or projection matrix. Now camera center will be nothing but minus of M inverse P4. Okay, so whenever we will do this, we can get the camera center. So please remember this is inhomogeneous coordinate. So that is why we have a tilde over here. Okay, we have a tilde over here. So that is this thing. We have a tilde over here. So this is nothing but this is your C tilde means we will be getting our camera center in a inhomogeneous coordinate. Okay, so this is the equation. So we can get our camera center in a inhomogeneous coordinate. Okay, so very easy. M inverse you can easily find out. This is the M. Okay, minus 9 2 3 3 minus 9 6 and 2 6 minus 10. If we just do the M inverse of it, so this will be our inverse, this will be our inverse. This is actually the determinant to it, minus of 294, and this is the cofactor adjoint of it. Okay, so this is how we can find the M inverse. Okay, M inverse is nothing but 1 by M delta, that is M del, that is the determinant of the M matrix and adjoint of this matrix. Okay, so this is the adjoint and this is the minus 1 by this is the determinant. 294 is the minus 294 is the determinant. So this is the determinant and this is the adjoint. So we can get the this is the adjoint, and if we just simply multiply it by this P4, that is 1 1 1, so we can get the C matrix, that is the camera center. So is it clear to all of you how we got the camera center? Is it clear? Clear, right? Okay, I guess clear to all of you. It is very simple. We will be given a P matrix. So divide this P matrix into M and P4 matrix, and then what you do, minus of M inverse. So you just do the inverse of the M matrix, so minus of M inverse, and multiply it by your P4 column vector. So by that you can get nothing but your camera center, but it is an inhomogeneous coordinate. Please remember this, okay? It is not an homogeneous coordinate. That means this is the real coordinate, x, y, z. No scaling is here for it, okay? So this is regarding the camera center. Now next thing, that is vanishing of point x. So vanishing of point x we have seen in the previous discussion. What is the vanishing of point x? Vanishing of point x is nothing but our p1. So that means just p1 we can write. So what is the p1? P1 is nothing but this, minus 932. So this is nothing, minus 932 is our vanishing of x-axis. Similarly, vanishing of our y-axis will be 2 minus 9 comma 6. Now what is image at origin? Image at origin is nothing but this, okay? 1 1 1, that is p4. Okay, so this is p4 is the image point of origin. I have already told you this is the property, okay? Second property, this is the column point property, okay? Second property. So what I have told you, vanishing of x-axis will be p1, vanishing of y-axis will be p2, vanishing of z-axis will be p3, and p4 is the image of the coordinate of the origin. So vanishing of x-axis has been asked the question, so this is nothing but our p1, that is minus 932. What will be vanish image of point of origin? That is nothing but p4, that is 1 1 1. So very easy, p1 and p4, very easy. Now our fourth question, that is vanishing point of the line with the direction cosine 2 3 4. So vanishing point means we have to multiply p with a projection, p with some matrix, okay? So some matrix is for vanishing of x and y axis and z axis is 1, for x axis is 1 0 0, for y axis is 0 1 0 0, for z axis is 0 0 1 0, for this image point at origin 0 0 0 1. And now if we are given the direction cosine, we can easily multiply it. Direction cosine is 2 3 4, so we can multiply it by 2 3 4 0 and transpose of it. That means this projection matrix is 3 cross 4, okay? 3 cross 4 means 3 rows and 4 column. Now why we are doing the transpose of it? Because our 2 3 4 0 is a row matrix. That means it is actually 1 cross 4, but 1 cross 4, if we just multiply it, what will happen is our matrix is we cannot multiply our matrix, okay? So that is why we have to change it in 4 cross 1. Okay, how we can change it into 4 cross 1? By simply doing the transpose. So that is why we are doing the transpose over here. So 2 3 4 0 transpose of it, and we will be getting the answer 0 3 minus 18. Okay, because 3 cross 1 we will be getting 3 cross 4 into 4 cross 1, that is nothing but 3 cross 1. So 0 3 minus 18 we will get. So is it clear to all of you? Exercise 1. Yeah, please.
Sir, here I'm not clear about cofactor matrix.
Cofactor matrix. So you have
Yeah.
to refer to your matrix of the 12th class. So what is cofactor matrix? Cofactor matrix is okay. So let me show you by one thing, so it will be clear. So this is your M matrix, right? This is your M matrix, minus 9 2 3 3 minus 9 6 2 6 minus 10. Okay, now how you can get the cofactor of this element minus 9? So what you do, you just hide this line and you just hide this line. So what you are left with, this and this, right? So minus 9 into minus 10 it is 90, right? 90 minus 36, that is 54, right? 54. And 54 is nothing but minor. 54 is not cofactor, 54 is actually minor of this element. So how we can get the cofactor of it? Cofactor is minus of 1 I plus j. Okay, I plus j is in power. Okay, I plus j. What is I plus j? I plus j is the indexing of the element. So what is the indexing of the element? This element minus 9 is present at position 1 comma 1, right? This is at position 1 comma 1, so I will be 1, j will be 1. So minus of 1 plus 1, so that is minus 1 of power 2, so that is 1. So that is why our cofactor will be equal to minor, that is 54. So now is it clear how we can get the cofactor matrix for all the points?
Yes, sir. I remember.
Okay, so let's again take an example of another point, so it will be more clear how we can get the adjoint cofactor of this minus 9. How we can get the cofactor of minus 9, can you tell? How we can get cofactor of this minus 9? We have to, what we have to do, we have to hide this and this, right? So minus 9
Yes,
into
sir.
10, so that is 90, right? 90 minus
84.
6, 90 minus 6 is 84, right? 84, and
Yes.
our this minus 9 is at position 2 comma 2, so that is why minus 1, 2 plus 2 is 4, so that means minus 1 will become plus 1, and our cofactor will be equal to minus, that is 84. So you can see this 84 over here. Okay?
Okay, sir.
Okay. So by this you can find the cofactor of all. And what is adjoint? Adjoint is nothing but transpose of the cofactor matrix. So this is what? This is actually transpose of it. Okay? That means the rows will be converted to column, and column will be converted to rows. Okay? So that is the thing. This 54, 42, 36 will be converted to this. So that is why transpose of the cofactor matrix is your adjoint matrix. And adjoint divided by your this determinant of M will be giving your M inverse. Okay? So now M inverse, how to compute M inverse, is it clear to all of you? Clear, right? Okay, and this question is clear to all of you, right? So what will be the vanishing point of the z-axis? Can anyone tell me? Come on, vanishing point of the z-axis?
P into 0 1 0 0 1 0.
Yeah, so that will be P3, right? Yeah, exactly, P3, right? And vanishing point of the y-axis, P2. So P3 is 3, 6, minus 10. Okay, so that will be your vanishing point of the z-axis. Okay? Okay, nice. So I hope this question is clear to all of you. Let's move on to the next question. Okay? Exercise 2. So consider the following projection matrix of an optical camera based on the imaging system given a image point 2 comma 7. Okay, so 2 comma 7 is nothing but your small x comma small y. Okay, in r square. R square means real coordinate. Okay, and compute its corresponding scene point if it is known that point is at the distance 40 units from the center of the camera. Okay, so we have to compute the scene point if we are giving the image point. Okay, so can we compute it if it is given, if it is at a distance 40 units from the center of the camera, means 40 is nothing but your f is given, f equals to 40 is given. And second question is compute the principal plane of the imaging system. Okay, so can we do it? So let's see. It's very easy actually. So how we can do it? So this is your this is your projection matrix. Okay, projection matrix, again we have divided into M and P4, and from this we can calculate the center of the camera matrix. Okay, the center of the camera, that is same thing, minus of M inverse P4. Okay, so from this we can compute the M inverse, and if we multiply it by the P4, we can get the center of the camera. Okay, now if we got the center of the camera, how we can get the given a image point on the distance 40. So how we can get the scene point out of it? We can get the scene point out of it by nothing but by this you can say by this parametric equation. Okay, how we write this parametric equation? this 40 is the actually focal length, that is also given by mu. So that 40 we know, and we know the camera center. Okay, so x can be calculated by camera center plus your focal length into the direction coordinate of it. Okay, so how we can get the direction ratio? Direction ratio can be given by this. Okay, that is the m inverse into your image point in the homogeneous coordinate. Okay, because m inverse is in homogeneous coordinate, so we have to convert this 2D point into the 2D real space point into this homogeneous point. So that is why 271. So by this we are getting the direction ratio. Once we have camera center and we have this 40 units, the point is at 40 units, is at a distance 40 units from the image center. So we have camera center, we have the scene point, that is 40 units from the camera center, and then we can just multiply it by the direction ratio. Okay, so direction ratio or the direction of it. So it is nothing but this c. Okay, c tilde plus you can say mu into the direction. Okay, mu into n, mu into, let's say this is a direction, and what is this direction? This direction is nothing but that is given by lmn root over l square plus m square plus n square, that is direction. Okay, so lmn, we can find out the lmn, and if we find if we just do the mod of it, this lmn is nothing but your vector, right? But to convert into a direction, we have to divide it by the determinant of it. Okay, by the determinant of it, that is why root over l square plus m square plus n square. So by this we can get the nothing but your, we can get your scene point or the scene point from the image point. Okay, so what does this question actually signifies is that in the previous lecture, what we have in the previous lecture or previous week, we have discussed regarding this homogeneous matrix. Okay, the thing about homogeneous matrix is it is invertible. Means if we are doing a homogeneous transformation from one point to the next point by a homogeneous matrix, we can reverse back to the previous point. So that is regarding the homogeneous transformation. Now in case of this image and projection matrix, this projection matrix, whenever we are doing projection of a real coordinate, it is actually non-invertible. Okay, so that is why we have to actually, that is why we have to take the help of this parametric equation, because it is it is actually invertible. Why it is invertible? Because you can see it is 3 cross 4 matrix. Invertible matrix is always a square matrix. It is not a square matrix, so we can not just do p inverse of this point 271. That we cannot do. Okay, so that is why we have to go by this way, that is by this parametric equation form. Okay, now about option B, what have we told? Compute the principal plane of the imaging system. I have told you how we can compute the principal plane of the imaging system. That is very easy. That is R3T x. Yeah, this one. Principal plane R3T x equals to 0. So x we got from this. Yeah, x we got from our first 2a. From 2a we got the x. We have the x and we have the R3T. R3T is nothing but this thing. Okay, this thing. So we can easily get the you can say we can easily get the principal plane. Okay, that is nothing but you can say that is nothing but the last row of the P matrix. So that is why 1 minus 5 8 1. Okay, so that by that we can get the principal plane of the imaging system. So is it clear to all of you? Why we have taken the parametric equation form? Because actually P matrix is non-invertible, because it is not a square matrix. As it is not a square matrix, so it is not invertible. So we cannot directly do P inverse of this small p. That we cannot do. Okay, we can do to get the small p point or get the image point from the capital P point. We can okay, so this p is confusing, so let me say x and capital X, small x and capital X. So how we can get small x from capital X? Small x equals to p into capital X, right? It is very simple. So if we want to get capital X, you will say we will do P inverse of small x, we can get this, but actually we cannot get by P inverse of capital X, because P matrix is actually non-invertible. So that is why we have to take the help of this parametric equation, okay, to get the capital X. Okay, once we got capital X, the image, the principal plane is nothing but R3Tx. So x you know, and you just do R3Tx, and you will get the you will get the principal plane. Also, if you are given a projection matrix, the last row of the projection matrix is your nothing but your principal plane. So instead of doing R3Tx equals to 0, you can easily write as the last row or the last row of this as a principal plane. Okay, so this is the concept behind it. So have you understood what we have done and why we have done? It is clear, right? Is it clear? Am I audible? Okay, nice. So let's move on to the next question, that is the question number 3. Okay, exercise 3 or whatever, question number 3. So consider the following matrix. This is the P matrix. So consider 4 image points. This are the 4 image points: x1, x2, x3 and x4. These are image point, not the real point. Okay, these are the image point, that is points formed on the image plane. Let the camera center be denoted as O. Okay, compute the dihedral angle between the plane OX1, x2 and OX2, x3, x4. A dihedral angle of the two planes is the angle between their normals. So what we have to do? We just need to calculate. We just need to first form the equation of the plane. Once we form the equation of the plane, we can get the angle between the two planes. So how we can get the equation of the plane? We can get the equation of the plane OX1, x2 by simply whenever we are doing x1 cross x2, will be getting a line, and whenever we are actually doing the projection of a line, we are actually getting a plane. So that is the theory. So again I am repeating, in the previous class what we have seen, whenever we are doing cross product of 2 points, we are getting a line. Okay, so cross product of 2 points will get a line, and whenever we are doing the projection matrix, projection camera matrix multiplied to this line, we will get a plane. So this is the theory behind this. So very easy. If we can get the line from this 2 point x1, x2, so how we can get the line from x1, x2? Just do the x1, x2, just do this x1, ijk, okay. For this x1 we have 2, 5 and 1, okay, and this for this x2 we have 7, 9 and 1. Okay, 7, 9, 1. Last one is nothing but for scaling. Okay, so this is the thing. So ijk 2, 5, 1, 7, 9, 1. By this we can get the x1 cross x2. Whenever we got the x1 cross x2, just multiply it by P transpose. P transpose, we are simply doing the transpose because it is 3 cross 4 matrix, and our thing will come as 3 cross 1 matrix. So to convert it into 4 cross 3 matrix, we are just doing the transpose of it. So just do the transpose of it. That means row will be converted to column and column will be converted to row. Okay, so P transpose into the equation of this line will give us a plane, equation of the plane. So this is actually equation of the plane. Now again, to get the direction, what we do? We just divide it by the determinant of it. So just divide it by determinant of it and we get the direction. Similarly, to get a plane from this 2 point x3, x4, again first we will form a line between x3 and x4 by simply cross product of x3 cross x4, we will get a line, and then whenever we will multiply it by the projection matrix, we will be getting a plane pi 2. And then what we can do, we can just take the det of it and we can get the direction of it. Okay, direction of plane is nothing but the normal of the plane, because line direction, wherever the line is, the direction of line is same as the direction of line. But plane, in case of plane, this is the plane, your normal is actually the direction of the plane. So that is why we are taking the normal. Normal is nothing but whatever you got, you just divide it by that of it. So we got the n1 cap, we got the n2 cap, and theta is very easy, that is cos inverse n1 cap dot n2 cap. So by this we are getting the angle between the two planes formed by the two lines on the image plane. Okay, so is it clear to all of you? Clear, right? Is it clear? At least you got the steps of it. You are given 4 points, right? From 2 points you can form one line, from another 2 points you can form another line. Okay, and whenever we are doing the projection of that line, we are getting a plane. Whenever we are doing the projection of another line, we are getting another plane. Okay, now we have two planes, so we can easily find out the direction between the two planes. So that is the logic behind it. Okay, so by this, let's move on to the next things. So what we are left with? We are left with a concept called camera at infinity. Okay, so camera at infinity, in the previous homogeneous matrix also we have discussed about camera at infinity, or the affine camera. Affine camera is nothing but camera at infinity. Okay, so camera at affine camera, this is the characteristics of the affine camera, that is the last row. Okay, last row will be 0 0 0 1. So that is the characteristics of the affine camera. Okay, so what does this means is, principal plane will be at plane at infinity, camera center will lie at plane at infinity, point at infinity will also map at infinity, and parallel lines remain parallel after projection. So these are some of the properties of the affine camera. Okay, now why we are studying this affine camera? Whenever we are talking about the affine camera, so this will be our projection matrix. So earlier I have told you what will be the DOF of the projection matrix. It is actually 11. Okay, 12 not 12, because one element is for scaling, so that is why 11. But now you can see this 3 elements are 0. So that is why our DOF will be yeah. Any questions? Okay, yeah. So that is why our DOF will be 11 minus 3, because these 3 elements will be 0 in case of affine projection or affine camera. Okay, so these 3 elements are 0. So earlier our DOF was 11, right? But now our DOF will be 11 minus 3 equal to 8. That means now we will have 8 independent variables. So to solve 8 independent variables, earlier we have 11 independent variables, that is why we require 6 points to solve the projection matrix. Now we have 8 independent variables, so we will be requiring only 4 points to solve this projection matrix. So this is the theory behind it. Okay, so affine camera, affine projection or affine camera projection matrix, we will have 8 DOF. For 8 DOF, for each point we will be getting 2 equations. So that is why for 4 point we will be getting 8 equation. By 8 equation we can solve this 8 DOF. So that is why here we will have we will require 4 point of correspondence. Okay, but in general, if it is not a affine camera, then we will have 11 DOF, and for that we will require 6 point of correspondence. So this is the difference between our normal camera and affine camera. Okay, so this is the logic. Now we will have another thing called projective camera on a plane. So projective camera on a plane, what it is actually, yeah, projective camera on a plane. Yeah, this is the equation of a plane, and if your z is 0, that means your plane is at the principal plane only. Okay, so at that time what will happen is, this third element will be or your point will be at the your point is at the principal plane. So what will happen is, the z will be 0. Okay, so the z will be 0, so that is why our point will be x, y, 0, 1. 1 is nothing but for scaling. Okay, and this is nothing but your projection matrix. So your point on point your point on the image plane will be equal to q equals to pq. P is the projection matrix and q is the point. But the important thing about this point is we are talking about point at the principal plane, so that is why the z is 0 for here. So as the z is 0, term, or you can say this is known as projective camera on the plane, because we are talking about point at the principal plane. So your q will be equal to this, and in this case what will happen, this p3 the effect of the p3 will diminish. Okay, so we can write this as p1, p2, p4 and x, y, 1. Now when it becomes p1, p2, p4, that means we are subtracting one column, that is the p3 column. What will happen is this is actually becoming our homogeneous matrix, because homogeneous transformation matrix, I have told you homogeneous transformation matrix is of the order 3 cross 3. Now this matrix is 3 cross 3. Now we can easily write it as homogeneous matrix. Okay, and this is q pi is nothing but this x, y, 1. So this is the thing. So small q will be equal to h of q pi, that is q pi is nothing but this point at the principal plane. So this is the theory behind it. Now we have another theory, that is projective camera on a line. So you can see this is the line on the image plane, and it can be easily denoted by xt, l equals to 0. This also we have discussed in the previous class, that is the transpose of the point into the l or the line vector, that will be equal to 0. Okay, now as we know how this xt is formed, this x is formed by nothing but projection into the capital X point. So that is why p into x, t into l. Now if you just expand this, so it will be equal to x of transpose p transpose into l. Now this p transpose of l is nothing but your plane. Okay, this p transpose of l is nothing but your plane. So what does this signify is, whenever we are talking about line in an image, it is actually a plane in 3D. Okay, this is what it signifies. So whenever we are talking about line in image, it is actually a plane in 3D. And whenever we are talking about point in image, it is actually a ray in 3D. Yeah, it can be a point in 3D, but you know that the point can be at any distance. So that is why it is a ray in 3D. So this is the interpretation of this two things. Okay, this is nothing but just how your projective matrix can be turned into a homogeneous matrix if your point on the real space or point you want to transform is at the principal point, or z, capital Z equals to 0 in that case. And about this, whenever you are talking about line in the image plane, that is actually a plane in 3D. That is what we have done in this equation. Okay, so actually by x1 cross x2 we are getting a line, but whenever we are doing the projective transform, we are getting a plane. So that is what it has been shown here. Okay, that is what it has been shown over here. So is it clear, the theory portion? Affine camera, your 11 degree of freedom converted to 8 degree of freedom. 8 degree of freedom means 8 equations. 8 equations means you only require 4 corresponding points. Okay, and then point in the line in the image plane is actually a plane in the 3D. Okay, so these are the two things. So I hope it is clear to all of you. And if we just remove the P3 or the third column, actually our projection matrix will become a homogeneous matrix, homogeneous transformation matrix, that we have discussed in the previous class. So I hope it is clear to all of you. Let's move on to the next thing, that is the last thing on the last portion of the theory, that is regarding vanishing points. So vanishing point is nothing but if you do the projective transformation of a point at infinity, and how a point at infinity is denoted by this d comma 0, because 0 is the scaling. So whenever you do the d by 0 of any point, that is x by 0 you do, or y by 0, it will be infinite. So d0 is how we write the x at infinity point. and if we do the projective transformation of it, we will be getting this. Okay, so what is vanishing point? Vanishing point means in the real space, if you see the point parallel, okay, actually in image plane it can parallel and it is not meeting at the point. Actually in the image plane it can meet at a point, so that point is nothing but your vanishing point. So this P means you are actually doing some kind of transformation into another plane. So in that plane uh, actually the points which are not meeting, okay, that points can meet in that plane. So that is the vanishing point. Other theory you need not to just remember. Just remember this x infinity you have already read in the previous class also, that minus b comma a comma 0, that is nothing but your coordinate of a point at infinity, right? So same thing here it has been written as d0. Last scaling will be 0 in case of vanishing point. You do the p of it and you will be getting a vanishing point in the image plane. So that is the simple thing. Now about vanishing lines. Vanishing line is the image of the horizon for a plane in 3D and its projection of all the points and infinity lying on the given plane. So again, no need to understand all this, just you do the PTL. So if L is nothing but your vanishing line, so you will get a direction. Okay, you will get a direction, or rather a plane regarding the vanishing line. So your this line, if it is at image plane, this vanishing line if it is image plane, so actually in 3D space you will get a plane, and this plane is known as image of the horizon. Okay, so let me solve one question, it will be more clear. So this, suppose the camera has the following matrix P. So P is given, so you have been given a line L. So this has been a line 3x plus 4y equals to 5. That means 3x plus 4y minus 5 equals to 0. So what will be your coordinate? 3, 4 and minus 5 of the line. Okay, so simply you do pt into L and you will be getting a something this n vector. Okay, and you just do the determinant of it, divide by determinant of it, and you will get a vanishing line. Because why vanishing line? Because it has been told compute a normal of the plane which the line appears to be horizon. That means vanishing line, you have to do the plane comprising the vanishing line. So that is plane at the horizon. Okay, so that is nothing but this thing. So is it clear to all of you? Clear, right? Line, you just do the p transpose of the line and you will get a plane. Simple, that is the simple concept. And if this line is nothing but a vanishing line, you will get a plane at the horizon. Okay, that is the simple thing. So you need not to understand anything in case of question. Whenever you have been asked to compute the normal of the plane which the line appears as the horizon, what you have to do, you just have to take the line, you just multiply it by p transpose, you will be getting a n. You just do the you just divide it by the determinant to get the direction, and you will be getting the answer. Just simple thing. So is it clear to all of you? Clear, right? Okay, nice. So by this, let's move on to the questions. So yeah, this last is the summary. So all this I have discussed again and again, so I am not repeating it. It is summary. So you can see this pinhole camera, then projection matrix. There's 3 cross 4, 11 DOF, 5 intrinsic parameter, 6 extrinsic parameter. What is affine row? This DOF will be 8, and all this thing. Camera center, this is the formula for the camera center, and this are the vanishing point of x-axis P1, y-axis P2, z-axis P3, image of world origin P4, and then principal plane, that is the R3. Okay, R3 is your principal plane, and all these things. So I have discussed again and again, so let's skip this. I hope it is clear to all of you. Let's move on to the question. So for today's topic, your question will be regarding the camera geometry, pinhole camera mapping, offsetting principal point shifting world coordinates, CCD camera model, projective camera matrix and properties, camera parameters from projective camera matrix, projective camera on the plane and line, and camera at infinity, affine projection, vanishing point and vanishing line. Okay, so this is well. So let's directly move on to the question. Again, I will be happy if you will just guess the answer first, or you can just say, yeah, can you solve assignment 2 second question? Okay, I will see after this session. Okay, so yeah. So yeah, I encourage everyone. So first to please guess the steps, at least guess the steps, and then we will be discussing the answer. Okay. So consider the projection matrix P. So this is the projection matrix. Evaluate the camera center in the homogeneous coordinate. So can you do it? Can anyone tell how to do it? Camera center. Can anyone tell how to do it? Come on. Unmute yourself and can anyone tell? Very simple. We have discussed it, right? Whenever you have been given P, how to find the camera center?
M inverse into P4.
Yeah, minus M inverse P4, right? Minus M inverse into P4. So very simple, right? So what is M is here? This portion is the M and this portion is the P4. Okay, this is M, this is P4. So just find the, this is M and this is P4. Just find the M inverse. Okay, how you can find the M inverse? This is how you can find the M inverse. So this is actually the M inverse P4. Yeah, this is actually M inverse P4. Here it has been written the camera center in homogeneous coordinate. Whenever we are doing this, our C is coming at C delta. That means C del. That means M inverse P4 will give us C tilde, means inhomogeneous coordinate. But whenever we are talking about homogeneous coordinate, we have to add 1 to it, 1 to the last element. Okay, so this is actually our answer, but it is an inhomogeneous coordinate. To make it in homogeneous coordinate, we just have to add 1 here. Okay, so our answer will be minus 1 by 3, minus 4 by 3, 1 by 3, 1. So our answer will be option A. Okay, so is it clear to all of you? Clear, right? Okay, nice. Yeah, so let's move on to the next question. If the principal point is located at 3, 4, okay, in coordinate system of the image plane, what would be the image coordinate of the world point 1, 2, 5 using a pinhole camera, focal length f equals to 0.5. So any guesses how we can do it? Any guesses? How small x is calculated? Small x equals to f into capital X by z, right? Small y, how we compute small y? Small y equals to f into capital Y by z, right? But here it has been told us not to find xy but x dash y dash. What is x dash? X dash is px plus x. Y dash is py plus y. And what is px py? Px py is nothing but px is 3 and py is 4, because px py is 3, 4. Okay? So now is it clear? So I hope it is clear. So let me show you the answers. Yeah. So xy, this is actually xyz. Okay, capital X, capital Y, capital Z. This is f, right? And this is px py. What we have been told? We have been told to calculate x dash y dash. What is x dash? X dash is px plus x. Y dash is py plus y. So what is x? X is f capital X by z. What is y? F capital Y by z. Okay, so this is x dash, x or x dash, whatever you tell. So let me make it x dash and let me make it y dash. This is y dash. Okay, and this is actually x, f capital X by z. This is x, f capital Y by z. This is y. Okay, so x dash equals to x plus px, y dash equals to x plus py. Everything it is been given. Px py is this, so it is very easy. Okay, so x you can calculate. This is coming 3.1, y is coming 4.2, and our final coordinate is 3.1, 4.2. That is option C. Okay, so is it clear? Is it clear to all of you? Yeah. Yeah, so let's move on to the next question. Find out the direction of the principal axis of the camera with projection matrix P. So can anyone tell? Direction of the principal axis.
The last row of M will.
Yeah, last row. Very good. Last row of P. Okay, so what is the last row of P? This. Okay, but this one is for scaling, so this is actually the direction. Okay, 2 0 0. Okay, so option C is your answer. Okay, sorry. Why this pen is like this? Yeah, option C is your answer. Okay, so option C is your answer. So very easy. This is the P matrix and direction of principal axis. This is given by M3. Okay, this is M3. That is true. 0 0, or the third row of the M matrix. Okay, this is the M matrix and this is the P4 matrix. Okay, P4 matrix or P4 vector. So the last row of the M matrix will give you the direction of the principal M axis. That is 2 comma 0 comma 0. Okay, so this is the answer. So is it clear? Clear, right? Straightforward question. So let's move on to the next question. A projective camera. This is the projective camera image. Images a 3D line. This L. Okay. Compute the plane found by the projected line L and the camera center. So can we do it? Can we do it? PT L, right? P transpose into L. Very simple, right? So yeah, P transpose into L. So plane will be found by P transpose into L. So P transpose, just do the transpose of it. That means column will be converted to row, row will be converted to column. Okay. So PT and L is already given. That is 5 to 7. So whenever you will be converting into PT, that is transpose of it. So earlier it was 3 cross 4, but after converting into transpose, that is 4 cross 3, and this will be 3 cross 1. Okay. So your answer will be coming. Your answer will be coming like this. Okay. So it is very simple. Okay. 4 cross 3, 3 cross 1. So your answer will be coming 4 cross 1. Okay. Your answer will be coming 4 cross 1. So this is the you can say this is the equation of the plane. Okay, 56 12 87 0. So option B is the answer. So again, nothing, very easy. PTL. Okay, whenever you are given a line, the image plane, and you want to get a plane in the real plane, nothing. What you do? P transpose into L. So L is given, that is 3 cross 1 is given, and this is this is actually 3 cross 4, but convert into transpose, that will be 3 cross 4. So 3 cross 4 into actually it is 3 cross 4, but now it will be 4 cross 3, 4 cross 3 into 3 cross 1, that will be equal to 4 cross 1. So this will be 4 cross 1 matrix, or 4 cross 1 that column vector will be your pi. Okay, or the equation of the plane. So is it clear? Very easy. PT into L. Okay, PT is the transpose of the projective camera matrix into the line. Okay, so this is regarding question number 4. Now let's move on to the question number 5. Okay, so consider a camera centric world coordinate system of the image plane parallel to the principal plane. Okay, that means we have not shifted the real coordinate. Okay, shifting has not been taken place. It is x and y coordinate axis parallel to those of the world coordinate. That means shifting has not been taken place. Okay, if the principal point is located at 2 comma 5, that means we have px py, that is 2 comma 5 in the coordinate system of the image. What would be the projection matrix in a pinhole camera with focal length f? So it is simple. How it is simple? It is actually this matrix. So let me show you. This is this matrix. Okay, last matrix, that is offset of the principal point. This matrix. Okay, this matrix. So this matrix will give us the projective camera matrix in case of that. Okay, so that is f0 px0 0 fpy0 0 0 1 0. Okay, so you have to check what matrix it is according to the options given. So just check it. What is the question? This question, right? So so this is the thing. So let me show you. So f0 px0. So f, what is f? F has been given 3. So f0 px0, px is 2. Okay. So 3020, 3020, 3020. So I think option A is the answer. And let's check another row. So 0f py0. So 0 3, yeah, 3 is the py is the 5, yeah, py5 0 and 0010. So option A is the answer. So is it clear? Just plug in the value and you know the projection matrix in case of just offset of the principal point. Okay, not shifting of any real coordinate. Okay, shifting of the world coordinate. Shifting of the world coordinate has not been taken place, so just the projective camera matrix will be taken from that just offset of the principal point, and that is f0 px0, 0f py0, 0010. F is given, px py is given, just plug in the value and we will get the matrix. Okay, and that is option A. So is it clear? Okay, nice. So let's move on to the next question. So next question, consider the camera projection matrix P, two image points x1 x2 and the camera center O. Find the unit normal plane O x1 x2. Very easy, right? So how we can do it? Can anyone tell how we can do it? What is the step? Come on, we have solved it, right? So from x1 and x2 2 points. So from x1 and x2 first we will make a line. How? x1 cross x2. Then what we will do it? Whenever we got a line, okay, so we will do
And divide with P transpose.
yeah, P transpose into the line. So by that we
And
will
then
be
we have to
getting
find
a
normal.
yeah, and then we have to find a normal, that is divided by determinant of it. So very simple. So let me show you the solution. So yeah, this is the projection matrix, and yeah, this is the projection matrix. Simple, you do the, these are the 2 points x1 and x2. Homogeneous we can write 2 5 comma 1, 7 9 comma 1, because homogeneous this is actually in a two dimension. That means this is actually in inhomogeneous coordinate. So to change it into homogeneous coordinate, just put it 1 1. You do the ijk 2 5 1 7 9 1. You will be getting the equation of a line. Once you got the equation of the line, so this is actually the equation of the line, minus 4 5 minus 17. When you got the equation of the line, what you do, just plug in the value, that is this is nothing but 3 cross 1 vector, right? 3 cross 1, and this is actually 3 cross 4. So just do the transpose, so it will be 4 cross 3 into 3 cross 1. So 4 cross 1, or you will get the 4 cross 1 or the equation of the plane. And now it has been told to find the unit normal. That means just divide it by determinant of it. So determinant of it you just divide, and you will be getting the approximate as 0.20, 0.50, 0.84. Okay, so 0.20, 0.50, 0.84. Option C is the answer. Okay, option C is the answer. So is it clear? It's clear, right? Another 0 can be written here, but as it is not given in the option, so that is why I have not written. So and the 0 can be written over here, but as it has been told only to find the unit normal direction, so that is why there is no significance of 0. Actually there will be a 0 over there will be a 0 over here, and there will be a 0 over here. Okay, so this is the answer, and there will be actually a 0 over here. Okay, so this is the thing, but as in the option 0 is not given over there, so you can write like this. Okay, so this is the answer. So is it clear to all of you? Clear, right? Okay, nice. Now let's move on to the next question. Perspective projective mapping is imaging the 3D world coordinate to an image plane using a projective camera where all ray passes through the camera center. Consider the center, camera center is 0 comma 0 comma 0. The image plane is parallel to xy plane, that is good, and at a distance of f from it, the perspective projective mapping from the world coordinate 1 4 5, so that is capital X, capital Y, capital Z, to image coordinate is small x, small y we have to find, and f equals to 0.25. And here there has been the image, there has been no information about offset of the principal point, so px py is not given, so we have to find only x and y. So x will be f into capital X divided by z, y will be f into capital Y divided by z. Okay, so again x will be f into capital X divided by z, y will be f into capital Y divided by z. So very easy, this x and y you can find out. F is given, yeah, f is given, x, this is y, capital X, capital Y, capital Z. So just plug in the values and you will get the small x and small y. Small x is coming 1 by 20, small y is coming 1 by 5. So option B is your answer. So is it clear to all of you? Here no information has been given for px py, so that is why no need to add px and py to it. Okay. Clear, right? Easy question, I think it is clear to all of you. So let's move on to the next question. So given a projection matrix this, compute the vanishing point of a line in the image coordinate with direction 4:3:2. Again this question we have done. How to do this? Can anyone tell? P into
432 transpose 4320.
yeah, so that thing. So it is very simple. We have also done at the example part. So this is nothing but the direction ratios. Okay, this can be written like this. You just do the P into this. Okay, P into this, P into D. So just do the P into D and you will be getting the this thing, whatever the vanishing point in the homogeneous coordinate. Okay, so this is actually 3 cross, yeah, this is actually 3 cross 4 and this is 4 cross 1, so you will be getting 3 cross 1. Okay, so this is the same question, you can just solve it like this. Same question, I have solved in an exercise. We have, whenever we have done the exercise, yeah, this question only, exercise 1 I think, yeah, this question only. Okay, vanishing point of line, this is the thing. So just do this P into the direction ratios. Direction ratio here has been given 2 3 4, there something direction ratio has been given, just do that and you will be getting the answer. Okay, so for direction ratio I have denoted the matrix as D. Okay, so that is the thing. Right, so very easy, that is P into D. P it has been already given, direction ratio has been given 4:3:2. So 4 3 2 and last is 0, because we are talking about vanishing point, and vanishing point the last is 0, because 0 means scaling 0, that means anywhere you will be divide 4 by 0, actually it is at infinity, 3 by 0 infinity, 2 by 0 infinity. So that is how we write we write regarding the vanishing point with the direction cosine. Okay, and P is already given, so just multiply into P into T and you will be getting a vanishing point. Okay, that is, so it is clear, right? Any doubt regarding this question? No doubt, right? And you can just divide it by the scale. Okay, so the scale is 10, so you can divide it and you can get the actual image point in the vanishing point, rather I can say vanishing point in the inhomogeneous coordinate, because here the option has been given in inhomogeneous coordinate. So that is 1.5. So option A is the answer. So it is clear, right, to everyone? Any doubt regarding this? Especially how we have written this point with the direction cosine 432. Clear, right? Yeah, nice. Now let's move on to the next question. We have been given this projective matrix P. Images are 3D line L. L this. Compute the plane formed by the projected line and the camera center. Very easy. Again, PT into L, right? That is P transpose into L. And this can be easily find out. P transpose into N, and we can get a plane with it. So P transpose, you just do the transpose of it, you multiply it with the line, and you can get the solution. Okay, so now it has been given 11 14 11 0. So option D is the answer. So again, same type of question, so that is why I have discussed quickly. So I hope it is clear to all of you, right? Whenever we are doing the projection, multiply a projective matrix with the line, we are getting a plane out of it, right? So this is the equation of the plane is P transpose into line. Okay. Now let's move on to the next question, that is find out the principal point in the 2D real space. Okay, 2D real space. Okay, please understand this. And principal axis vector of the camera matrix P. Okay, this is the P matrix. So these are the option A, option B, option C, and option D. So can anyone tell at least what will be the principal axis vector? Can anyone tell this part? Principal axis vector?
The last row
Yeah, that is.
and then multiplied with the k.
Yeah, that is
120.
120. Okay. And
So actually, I need two real space. You have to solve it elaborately. I have it out of that.
Yeah. So this is very clear to all of you. I can easily tell. This is very clear to all of you. Just do this, and you will be getting into just multiply it by the scale. So that is different thing. So this. Now what about principal point? Whenever principal point, so principal point is nothing but principal point is nothing. What you have to do for principal point, you have to do this m dot mq. Okay, so m dot mq. What is m? This is the m matrix. Okay, and what is m3? This is the m3, or the third row of the third row of the m matrix. Okay, so third row of the m matrix, you just do the dot product of it, and you will be getting this. Okay, you will be getting this. So just you will be getting this, and what you do is just divide it by scale, and you will be doing the divided by scale, and that will be equal to 15 by 5 will be equal to minus 15 by 5 will be equal to minus 3, 12 by 5 will be equal to 2.4. And this is already clear, that is the 120, that you know the principal axis vector. For this principal point, you just do this m dot mq. Okay, so whenever you will do m dot mq, you will be getting this. Okay, that is the principal point in the 2D space. So option A is your correct answer. So is it clear to all of you? Clear, right? Okay. So by this I am ending the session for today, but some of you were asking me the assignment of second question. Yeah, the answer is actually, I think there is an anomaly in answer. So as of I cannot do anything for that. What you do is just give in that question answer section, go in that question answer section or QA section of your this SWAM portal. You just show your concern that the second answer we are getting a different option, and they will be marking according to that. Okay, so that is the thing. And for so let me so let me show you the answer. Yeah, this is the thing. Okay, so I think this is the question. Okay, this is the question, right? Question number 2 or question number 1, whatever you are asking. I think this is the question number 1, right? So do you have the question with you? I think this is the question number 2. So this is the question number 2. Okay, so what you have to do to transform point of intersection into a homogeneous, different homogeneous plane, right? So how you can get the point of intersection? You have this two lines given, I think, minus 4x plus 4y plus 5 equals to 0. So this L1 you can get. L2 you can get by this, that is x plus 2y minus 2 equals to 0 is given to you. So you just do the L1 cross L2, you will get the point of intersection in one space. Okay, and now to transform it into another space, what you do, you have to apply the homography matrix. Homography matrix is already given. Can you send this document? This document.
Actually, answers actually not elaborately given in that assignment solution. That's why we are asking. Because they'll give only the equations. That's why we are there.
But you know the theory portion, right? That I
Yeah,
have already.
we know theory, but exactly not solve the step by step in answer session.
Right,
That's why,
step by step
because when you have to
given to you.
referring for examinations, it is very useful
Okay.
for us.
Okay,
That's why
so
we are asking.
for that I will be giving that in that folder only. Okay. So I hope at least you get the concept of it. Anyone who did not know the concept of it, can you please raise your hand or ask me if anyone is doubtful about the concept yet? So by two line, if we do the intersection of a two line, we get a point of intersection. Now what we have to do in the question, we have to transform that point of intersection from one space to another space. So to transform one point from one space to another space, what we do, we just multiply the homography matrix. So in this question, what we will do, we have L1, we have L2, we will do the cross product of it, we will get a point P. That is the point of intersection of two lines. Once we got the point of intersection of two lines, we just multiply it by the homography matrix. So homography matrix into the point of intersection, that will be equal to your point in the new space. Okay. So this is the thing.
Explain the third question solution.
Third
Because they are
question.
asking previous transformation. How can you get it?
Yeah, previous transformation. So yeah, so same thing. So p dash will be hp, right? So p dash is given, so p you have to find. So p will be h inverse of p dash. Okay. So have you got the theory behind it? So
Yeah,
this
okay,
is,
okay.
yeah, this is the thing. So yeah, this I can keep it if you say. If you say, I can keep it in that document folder wherever I give you all the slide and all. There I can keep it if you will say. Okay.
Yeah, okay, sure. Thank you so
Okay.
much.
So any else? So any doubt regarding today's lecture? Any particular doubt?
No, it's the last one only. It was clear. No problem.
Okay. Okay. So by this I am sending the session for today. I am ending the session for today, and we will be meeting on the next Friday. Okay, next Friday same time 6 to 8 p.m. Okay. Okay. So thank you all of you. We will meet on the next Friday same time 6 to 8. Okay. Okay.